The purpose of this lab is collecting observational data of a magnet falling through a conductive tube of aluminum foil, modeling the magnet or tube interaction computationally, and comparing computational predictions with experimental data. The main physical principles involved in this lab are the Biot-Savart law for conductors, magnetic flux, and Faraday's law, as well as Newton's laws and Ohm's law. Experimentally, the magnet was dropped through the aluminum roll, taking an average of 1.5 seconds to fall through the roll. Computationally, the magnet was simulated based on the data from Lab 3 and the roll from the experiment was replicated. It was estimated that the time it takes for the magnet to fall through the tube is roughly 2.9 seconds. The bar magnet behaves as a magnetic dipole, creating a pattern of magnetic field around it that looks like a pattern in the figure. The magnetic flux can be defined as the amount of magnetic field passing through a surface. In this case, there is magnetic flux going through the aluminum foil as it is held over the roll. As the magnet falls through the roll, there is a change in the magnetic flux caused by the change of magnitude of the magnetic field. Due to Faraday's law, this change in flux generates an electromotive force, inducing a current on the aluminum roll. The current induced in the roll produces its own magnetic field. The magnetic field, according to Lenz's law, avoids the change in nature. Thus, this field produces an upward force on the magnet. The magnet, now acted upon by the forces of gravity and due to the induced current in the roll, falls slower than it would in free fall. For this experiment, we need a roll of aluminum foil and a standard bar magnet. In the setup, the system is a bar magnet, while the main elements of the surroundings are the roll of aluminum and the earth, which exerts forces on the falling magnet. First, using a meter stick, we take some measurements of the aluminum roll, including its length and the thickness of the foil. To perform the experiment, we keep the aluminum roll vertically. Then we hold the bar magnet above the roll and, while recording, we let the magnet fall through the tube. We register the time that it takes the magnet to fall through the tube. The time taken for the magnet to fall through the roll was recorded. The measured times were 1.69 seconds, 1.36 seconds, and 1.45 seconds. The average drop time was thus roughly 1.45 seconds. Onto the computational model, we first define some fundamental constants and we create a graph. Then we create a tube object by defining its properties such as its length, width, or inner radius, and the thickness of the foil. Now we create the bar magnet object by defining its mass and its magnetic constant. After that, we calculate the field generated by the magnet, and then we calculate the flux through the aluminum roll caused by the magnet. Finally, the movement of the magnet is simulated by updating its position as well as the force the roll induces on it. With the simulation, we obtain the following graph. We can see that the magnet reaches a terminal speed of roughly minus 0.5 meters per second, and we can see that the time it takes to fall through the roll is 0.951 seconds. Some sources of error include the human error when recording time with the stopwatch, and also the friction due to the magnet being in contact with the cardboard tube that possibly slowed the magnet down even further, accounted for the longer fall in real time than in the simulation. If the resistivity is close to zero, according to Ohm's law, the current induced in the roll would have been much higher. This would mean that the force acting on the magnet against gravity would be stronger, making the falling magnet reach terminal speed much faster or even to float in an ideal scenario. The holes in the foil would cut the continuity of the current, and thus the magnet would fall at a faster rate because the magnetic force induced on the magnet would be weaker. In conclusion, the time for a bar magnet to fall through a conducting aluminum roll was measured both experimentally and through a computational model. The average fall time recorded experimentally was roughly 1.45 seconds, while the computational fall time was 0.95 seconds. It is likely that this difference is due to friction slowing down the magnet further in real life, as well as human error when recording time with a stopwatch. This experiment is, despite the imprecision, a good way of visualizing Faraday's law, as you can clearly see the magnet falls slower than it would on free fall.